All right, welcome back to Machine Learning 1. This is Lecture 18. This is a Northeastern University course called DS 4400. Now, I am Professor Wu, and today we're going to talk about LDA. I guess that's a typo right there. So in the last class, we talked about this concept called principal component analysis, or PCA. And basically, the key observation of PCA is that you have some data, and you want to project the data onto some line such that after the projection, it will look relatively close to the original, right? So you're trying to preserve the shape, the original shape of the data through a projection. So in this case, the data lives in 2 dimensions. But you can see the data in this example lives in 1 dimension. Okay? So from PCA, what we want to do is we want to find a direction, right? There are many directions we can draw the line, but we want to find a direction such that the variation of the data is maximized. Now, to measure the variation, we've gone through the idea of covariance matrix. The covariance matrix allows you to measure the variation for high-dimensional data. So instead of finding the covariance directly for the data X, what we could do is we could find the covariance after the projection. So V, this direction V hat, this is the projection. So after we've done the projection, we want to find the V such that the covariance is as large as possible. And then we went through a bunch of math and essentially showed that the covariance of X is equal to this equation. And therefore covariance of V hat, well, you just plug that in, right? So that's the insight to PCA. However, PCA does have a downside. So the downside is it's useful when we want to maintain the original shape. So over here, if you do PCA, obviously it's going to try to maintain the original shape so that after the projection, it looks like this. However, sometimes we don't really want to preserve the shape. We have an alternative goal. The goal in this particular case is to perform classification. We want to, and you can tell, it's very hard to separate out the orange and the green points after you do the projection. So you, in this case, you don't want to do PCA. Ideally, you want to project the data, in this case, something more that looks more like this. In this case, the data also lives on 1 dimension, right? 1 dimension, after projection. However, notice that the orange are nicely separated from the blue, the green. Therefore, like when you run like SVM, for example, you will be able to like draw a line and perform classification. So this is essentially the key idea to dimension reduction via LDA. You don't want to project such that you preserve the original shape anymore. You want to project it such that it makes it easy for you to do separations of data. And when you can make data separated, that's how you can tell things apart and perform classification. Okay? So PCA is unsupervised, which means you just have the data, you don't have any labels. LDA is a supervised method. So you are performing dimension reduction with the guidance of labels. Okay? So this time there's labels. So the goal is to find this like vector such that after the projection, right, things are separated. But how so? How would we like them separated? Well, in the LDA algorithm, we want to do the projection such that the same class will be pulled tightly together. So we want this to be really tightly jam-packed. And we want this to be tightly jam-packed. Meaning we want the variance we want the variance of the data in this class to be as small as possible, as well as this one. So we want the variance of A and B to be as small as possible. Okay. And second, we want the center of these 2 points to be as far apart as possible. So if we can make them far apart, then the farther apart, the easier we can essentially distinguish them, right? So if ideally we have them really far apart, right? Two groups really far apart, right? And this makes it easy to tell them apart. And we want them tightly packed. When they're really tightly packed, you can imagine if this is not tightly packed, then it's not good because they're too close to each other. So you want them tightly packed, and you want the center to be as far apart as possible. And that essentially leads us into the objective LDA. So this is the objective for LDA, and V here is the line which perform the projection. Now, just like PCA, where we're trying to find a line to project, LDA, we're also trying to find a line to project. So, looking at this equation probably doesn't make a lot of sense to you right now. And our goal today is basically learn the background story, like the origin story of this equation. How did it come about, as well as how do we actually solve something that looks like this. Okay, so the first step we're going to take is to make one realization on an optimization problem. And this essentially is the core solution to LDA. But let's look at it from a very simple case. First, in this case, we are projecting, right? We're doing a projection essentially. And both of them we're going to assume to be a unit vector. So the distance is on a circle, so right, on a circle. So every one of these is length of 1. We want what is the solution for this? So we have U, right? And we're projecting V. V could be this one, V could be this one. We're trying to pick the V such that after the projection, this whole thing is maximized. Okay. Now, you remember, I think I told you that when you perform like a dot product, it's equivalent to getting the coordinates of a projection. So if you're taking V here and you're taking the dot product U, and this is normalized, essentially when you take the dot product, you're going to get this value here. Okay? Or if V is this one here, this is V, you take the dot product, you're going to get this one. So, geometrically, if you look at it, which V should you pick out of all these such that you would maximize this entire thing? Well, hopefully you see the pattern that as you go closer and closer and closer to U, the projection distance gets larger and larger. And it gets the largest when V is just equal to U. All right. So if this is just on top of each other, then you're going to get 1. Whereas anywhere else, after you do the projection, it's going to be less than 1. So the solution to this is actually quite easy. That the maximum V you could pick is just U itself. Okay, so this is the logic towards this optimization problem. Okay, the second step is we've talked about eigendecomposition. We didn't really talk about in the video, but we talked about in class. Essentially, if you have a matrix A, if you can find the eigenvectors, so let's say maybe it has eigenvector v1, v2, we can let that be a matrix V. And with 2 eigenvectors, we get 2 eigenvalues, lambda 1, lambda 2. Okay? So from A, we can get a set of eigenvectors and a set of eigenvalues. Eigendecomposition is when you have a symmetric positive definite matrix. So if we assume A is symmetric and it's square matrix, then A, the matrix, could be broken down into the product of three matrices. So if you take the V here and the sigma here and multiply them together, you actually get the A matrix back. So what's happening is A is being decomposed into three different matrices. Okay? So and this matrix is always diagonal, where the off diagonal are always zero values. So that's where eigendecomposition came about. Now, the interesting fact about symmetric positive semi-definite matrix, basically matrix that are symmetric and have eigenvalues of always positive value or zero. Interesting fact about that is those matrix, you can always perform eigendecomposition. So if you can always perform eigendecomposition, it implies that you can split the sigma into 1/2 and 1/2. So the interesting thing about diagonal matrix is that if you have lambda 1, lambda 2, right, this is actually equal to lambda 1 square root lambda 2, 0, 0, lambda 1. So they're equivalent. Like if you just multiply them out, notice this and this would just give you lambda 1, and then 0, 0, lambda 2. Right? If you actually do the multiplication. So what is saying that when you have a diagonal matrix, it's really, really easy to break them apart. You can just break them apart into two of them through square root. So my point is, if you have a symmetric positive definite matrix, you can always perform eigendecomposition. And if you can always perform eigendecomposition, you can always split the diagonal matrix apart. Which means this is just the transpose of this. Therefore, I'm going to call this R transpose and R, like this. This part is R, this part is R transpose. So I think the key here is, if you have symmetric positive semi-definite matrix, you can divide them, decompose them into three matrices, or you can always decompose them into two matrices, right, where they are multiplication transpose of each other. So that's a very important point, assumption, that when you have symmetric positive semi-definite matrix. And again, symmetric, you already know what symmetric means. Positive semi-definite means their eigenvalues of the matrix A is always zero positive. Okay? So those are the matrices that we very often deal with. Okay, now here's an example. This is a matrix, and if you run eigendecomposition, you will realize you can break them into three. Like I showed you here, you can break them into three matrices. And guess what? If you were to multiply all three of them back together, it will reconstruct the original A matrix. Now, what's interesting, like I told you, is you can divide this into two more matrices, which they're just square root of each other. Hence, results. This essentially results us with the R and the R transpose, and R, like I showed you here. And guess what? If you were to multiply, so this right here, R transpose R, which becomes this. If you were to multiply these two, you will once again get the original. So this whole conversation is essentially telling you that under special cases, and symmetric positive semi-definite matrix are actually occurs a lot, so in nature. So I won't even say that's special. For these cases, you can always break the matrix into three. And if you can always break it into three, you can also always break A into two matrix of these form. So these two realizations requires you to understand eigendecomposition. And once you can break things into different components and you know the properties of those components, then you can perform like various manipulations, and like makes your life easier. So, like I told you previously, right? The LDA objective, it looks like this. I haven't explained to you yet the background story, how we got this. So, but instead, we're going to do it backwards today. Instead of learning the background story, then learn how to solve an objective like this, which is called the Rayleigh quotient. We are going to learn how to solve this first. Once we learn how to solve this, then I tell you how the objective came about. So this objective, like I told you, is called Rayleigh quotient, right? And we're going to make one key assumption, is that S1 and S2 are symmetric positive semi-definite. I just told you, if things are symmetric positive semi-definite, there are some special properties that can come along with it. Okay? So, the property that we're going to use is that S1 and S2, right here, S1 and S2, because they're symmetric positive semi-definite, we can always break them into two matrices. So S1 I'm going to call R1 transpose R1. S2 I'm going to call it R2 transpose R2, which allows us to rewrite this objective in terms of the S, right, becomes R1, and S2 becomes R2. Okay. Well, after this, I'm going to do a variable change. I'm going to just call R2 times V as U. Okay. Basically, I'm just going to rewrite this as U. And if we have this relationship, or we define this relationship, this is something we just define. Like, I'm going to just call R2V. This also implies that we could move U R2V. Right? If this is the relationship, we can multiply R2 transpose inverse, R2 inverse, and this gives us yet a different relationship, is equal to V. So right here. Now, why is that interesting? Well, we're going to now plug this V into here. Okay? Now, if I were to plug the V into all the V's here, right, then we end up getting this expression. So let's see if we can see that. I plug, I plug the V here. So let's write this out. V transpose R1 transpose R1 V. So V is equal to R2 inverse U. So over here would be U transpose R2 inverse transpose, which I think is identical to what I write here. All right, and now let's do the denominator, R2 transpose R2, and what is V? Is R2 inverse U, U transpose R2 inverse transpose. Okay, so R2 and R2 inverse cancels each other out, and this one is R2 transpose inverse, that cancels each other out, resulting in U transpose U. So that's how I got this part. Well, once you have this part here, when you have an inverse, a transpose of an inverse, you can flip them. That's one of the properties for matrix that I hope that you learn when you were in linear algebra. So if you can flip them, right? If you can, let me see. Is this what I did? R1, R1. So what I did is I combined them, and then, yeah. And then I moved the transpose out. So here's the transpose. Okay, so I combined this, I moved the transpose out, now we got this part. So this looks just like this now. And because they're multiplication of the same thing, we made that into a square. After we made it into a square, notice there's a square here. We can move both squares out. After you move both squares out, right, you can combine this, and that's just u hat. Okay. Now, this is a vector here. This is a vector. Or this is actually, no, this is some kind of, yeah, let's pretend this is vector for now. Now, does this look like something? Like, I'm just going to call this v hat, okay? So now we're trying to maximize v hat u hat. And we're trying to find the u hat that maximizes this. Well, we did this in the very beginning. This was one of the first things we did, is how do we maximize this? Well, it turns out that the solution is just v hat, okay? Or in this case, right here. This is your solution. Okay? So, what would be the u hat that maximizes this whole expression? Well, like I told you, then u hat must essentially equal to its complement component, okay, which is right here. And u hat is just essentially u multiplied by some constant. So if you take u hat multiplied by some constant, it gives us u back. Okay, so we can now represent u. But remember, we're not solving u, right? Ultimately, we were trying to solve for v. It's just that we kind of replace v with u. So now let's see if we can get v back. So we don't want u, we want v. We can try to get the v back using the previous equation. So this was that equation that somehow connected v and u together. So now that we know what u is, let's plug u into here. So this is the optimal u. If we have the optimal u, we plug it in here. Now we can get v. So we now have an expression of the optimal solution. Now, this is the optimal solution, but we can always make this look a little bit nicer. So let's take a look. Well, if we start off with this expression, which is the same as this, this means that once we put the transpose in, right, we flip the R2. So it's R2 transpose R1. So we flip the 2 when we are putting the transpose inside the brackets. Okay? So after we rotate them, well, we could put the transpose inside and put the negative one outside. So we can rotate these two. That's one of the properties of linear algebra. And now notice this is -1 on both of them. Well, this means that you could flip the 2. Okay? So all of these requires you to know the properties of linear algebra, of like when you flip inverse and when you flip transpose. So assuming you know that, then you move the inverse, right, outside of a bracket. Okay, once you move this outside bracket, R2 transpose R2. R2 transpose. Let's go back to the beginning. What's R2 transpose R2? Well, it's just that original S2 like matrix. So we can find it. R2 transpose R2. Right here. That's just S2. Right? S2. Therefore, I'm just going to put S2 here to make it simpler. So the optimum solution V is just equal to alpha, right here, just equal to alpha S2 inverse R1 transpose. Now, remember, you can get R1 from eigendecomposition, so you will need to know how to perform eigendecomposition. Now, alpha, we can actually just ignore it. It doesn't really matter, okay, because you have V in the numerator and V in the denominator. So you're going to have alpha here, which will cancel each other out. Don't believe me? Try plugging it in. You will notice all the alpha will cancel each other out. So the optimal solution can just ignore the alpha value, and it becomes V S2 inverse R1 transpose. So the solution to Rayleigh quotient. The solution to Rayleigh quotient. My eraser is not working. There we go. So the solution to Rayleigh quotient, which you are trying to find a V that maximizes the whole thing, is this expression here. Okay, we have a Rayleigh quotient, and we know how to solve it. Well, let's now go over the background story. How in the world do we get this objective in the first place? Well, projection and dimension reduction. Let's quickly go over that. Do you remember that when we project a vector V onto U, so let's say this is V, we're projecting onto U, so you essentially draw a line, and this point is P. So this is how you cast a shadow, right? After you cast a shadow, you can identify the point P. And the equation was that since P is just U alpha times some kind of constant, U alpha times some constant in order to reach P, so P is just U alpha times U times alpha is equal to P. And we learned that alpha is just the inner product between V and U hat. So we learned that in projection. Okay, so we learned all these already. Why am I repeating this? Well, there's some questions that raises to the surface when we are talking about dimension reduction and projection. Well, projection, remember from PCA, is used to reduce the dimension, right? So we're trying to reduce the dimension. But notice, why is the result of projection P still in 2 dimensions? This point is still in 2 dimensions, right? So that doesn't make sense. Also, when you project V onto 1 dimension, line U, when you're projecting onto this 1 dimension, shouldn't the result just be in 1 dimension instead of 2? So those are valid questions that we haven't really addressed in this class yet. And the answer is, remember that U just tells you the direction, right? You just know that U is the direction of a line, but alpha tells you how far you're supposed to go in it. After you perform projection, you don't really need to keep the line anymore. You can just ignore U hat and just keep alpha. You only really care about how far you're supposed to go, right? So notice on the right, see here we have the data, and if you perform PCA, it's gonna fall like this, right? So the data does live on a one-dimensional plane, and you can just assume that. And once you know the alpha value for every single one of these points, you can just put it on the x-axis. So you do only have one dimension as a result, which are the alpha values. So, because the alpha value just tells you how far you go. And then you can just assume it's on the x-axis, y-axis, whatever one dimension you want. It doesn't really matter. Okay? So, that's why in PCA, when we do projection, we are not actually following the projection equation here. Right? We're not getting the p-value. We're really just getting the alpha, which is also called the coordinate. We just really care about how far you go in this direction, the coordinate. Okay? So the key here is when you do projection, all you have to do is take the vector and do a projection to get the alpha. And we just need to keep the alpha. Okay? All right, now let's move on. In linear discriminant analysis, I previously told you the goal, right? We want to project the data points, each data point, onto a vector such that the distance between the classes are maximized. So you pick the center of one class, center of the other. We want this distance. We want to push the two classes as far apart as possible. Simultaneously, we want the variance of each cluster. So we want this variation to be very small. Okay? We want this to be as small as possible. So we want the projection that performs both of them simultaneously. And that is the difference between PCA and LDA. Okay? After PCA, you end up looking like this, which will make your life very difficult to perform classification. After LDA, it's pretty easy. Notice that the distance that pushed apart and the variation within the same class is minimized. All right, so the first objective is we want to move the center of two classes as far apart as possible. Okay, I'm going to first define S0 as consists of all the samples in group 0. Okay, so S0, I'm going to call that's all the samples are in S0. And there are N0 number of samples. So there are N0 number. So like 10 will be here, and this one could be 15, N1. So S1 is going to be all the samples. It's a set of all the samples in group 1. And the number of samples in there is going to be called N1. Now remember, we just really care about the alpha value. So each alpha value is just the projection of the sample onto the vector. I should have wrote the unit vector here. Okay? So that's how you get the alpha value. Therefore, if you get the alpha value, that's the result. That's the result after the projection. So after the projection, if you were to find the average of that point, it will give you the center. Okay, so for the cluster center 0, for this, you will average all the points and find the middle point. Again, you will average all the points for the green class and then find the center. So finding the center is pretty easy. So you project the data, then you find the center. Project the data, then you find the center. Now, after that, remember the objective. You want the distance between the center, right? The one minus the other. You want that distance, which L2 norm, you want that to be as large as possible. So you're trying to find a V that makes this the distance between the centers very far apart. Right? You want to find a projection V such that the distance between the centers are as far apart as possible. Now, I'm going to plug C0, C1 in. If you were to take the square, right? The first thing you, before you look at the square, first you look at V. Because V is the same, we can pull it outside, like such. V is pulled outside. Well, after you pull V outside, then we can take the square, which you write the expression twice, right? So after you do the square, this becomes V transpose. V goes to the other side. This becomes the transpose here. And I copy this again with the V. Well, guess what? I can just write this whole thing, which you know how to calculate. You know how to calculate the center, right? And you know how to multiply it twice by itself. So I'm going to call this whole thing S1. And voila, this is the objective, to maximize the center, to maximize the distance between the center of two classes. Okay, so this is the origin story. Next, let's work on the second objective, because they're dual objectives. First is you want to push them far apart. Second is you want these clusters to be clumped together as closely and tightly as possible. So, now remember, we've done this so many times. I keep going back to the equation of variance because it's used so much, right? Now, there's a parallel concept called scatter. Scatter is just variance without averaging. That's it. So that's scatter. So, now in LDA, right, you can remember we are trying to minimize the variance, right? You remember we want this cluster to be as tightly packed together. So, which implies you want the variance to be as small as possible. And therefore, if you just minimize the scatter, it's the same as minimizing the variance. So it's like the same equation without this. So we can easily calculate the scatter equation, which is right here. We take all the samples from the orange minus the center, and then over here is essentially the scatter equation. And conversely, over here is all the scatter equation for class 1, which is the green class. Now, we can calculate this, right? You know, at this point, you know how to calculate variance. But when the data becomes high dimensional is what we learned last class in PCA. Instead of calculating variance in high dimensional data, we want to calculate the covariance matrix, right? Covariance matrix. So we did all these things to learn that the covariance matrix, right, what it is. And we learned that the simplified version of writing the covariance matrix is just this multiplication. Now, covariance matrix has parallel equivalent for scatter, right? For scatter, it also has a matrix, and the only difference is they don't have 1 over n anymore. Everything else is the same. So you can calculate the scatter, right? So scatter is just the covariance matrix without the constants, right? Covariance matrix with the constant, right? Remember, C was that centering matrix that we did. And therefore, this and the scatter are almost identical. The only difference is a constant is left out. And that's it. So from this, we could calculate the scatter, right? We equate using this to calculate the scatter for class 0, all the pointing orange. So that's what I meant by x0. So class 0, all the pointing orange, as well as we can calculate the scatter. So if you have the data, right? Here's your data. Part of it part of it is going to be the orange, and part of it is going to be the green. So you take these orange, now you can calculate the scatter. And then you take the green, you can calculate the scatter again. And the total scatter is essentially scatter of the orange plus scatter of the green. So, and we're going to call that S2. So now that we know, right? Here's the equation. So scatter, the scatter equation we just saw for S0 is essentially, remember, we can make this matrix as vectors of vectors. So if I make this vectors of vectors, this is just x1 all the way to xn. This should have been a 0 here. So my point here is that if you want to do a projection, you just put a V here and a V here. Once you do the V, I don't think that is there. Yeah, I don't think that's there. So once you do the V, you can just project it down to every single point. You can project it every single point. So, and notice how if you multiply, if that's not there, V multiplied by each one of them, you are just going to get the coordinate. So the point here is this is a scatter. However, if you incorporate V in here, then that's the scatter after the projection with V. So that's the difference between the two of them. So now we have the equation for the scatter after projection for class 0, and you can follow the same logic and essentially get the scatter for class 1. And now we have the equation for the total scatter after projection, which is total scatter is the scatter of class 0, scatter of 1. We can pull the V's out. All the V's can be pulled out. This is missing a V here. V should be here. And I'm going to call this S2. Once we have S2, voila. So we now have a way, an equation to minimize. If we minimize this equation, then essentially you will make the scatter as small as possible for both classes. Okay? So that's what we're trying to do. We want to minimize this. So now we have two objectives. One is we want to maximize the distance between the centers. The other one is we want to minimize the, I want to say variance, but you got the point, the scatter between the two classes. The way LDA does is to combine them into one single equation. We put this in the numerator and we put this in the denominator. Notice that we are trying to maximize the numerator, right? And to make this big, we want the denominator to be as small as possible. Okay? And remember where we got S1 from, right? S1 was the distance between the center, and which give us R1, R1. And then S2 was from our total scatter equation. And that's the origin story of how this came about. Okay? We already previously learned how to solve the optimal Rayleigh quotient. So here's the Rayleigh quotient, and voila, here's the solution. So we learn how to solve it. We now understand where this equation came from, right? And that's how you will essentially solve LDA. Now, remember, I will beat on a dead horse. The R, you would use eigendecomposition. Eigendecomp. I keep coming back to eigendecomposition, and you will run into this over and over and over again if you want to be in machine learning. So the earlier you get good at eigendecomposition, the better if you want to stay in this field. So I wrote the code for you guys. This code here is actually LDA, step by step, like not the sklearn version. And the result of this code Let me show you. So this is the part that solve it with PCA, bunch of drawings. The point is that let's say we have some data. This is currently not centered. And I draw two lines. One line is the line PCA would have chosen. PCA would have picked this line. LDA, however, would pick this line. All right? And the result of PCA, you can see that it's essentially like all the points are just mixed together, and it will be very difficult for you to tell them apart with SVM. Alternatively, if you use LDA, wow, your life is much easier, much easier, because like with SVM, you can just draw a line here, right? And you're like, oh, well, everything that way is one class, everything this way is a class. Okay. Now, what I want you to do is, I think that's the last slide. Practice what we learned today. Right? Ideally, I want you to take this and don't look at my code. Don't look at my code. Only look at my code if you're like really desperate and really wanted. But don't look at my code and see if you can reproduce this. If you can reproduce this with both PCA and LDA, then you would really understand the ideas. And the derivation for LDA, which is the origin background story, I would like you to learn it. Right? And the math, if you were to step through them step by step, is not really that hard, really. Come on. I think you guys can do it. Now, the reason why I focus so much with you guys to tell you the background story is because I want you to actually know the background. The difference between a mediocre data scientist and like a great data scientist is whether they understand the background story. Because when you understand the background, that's when you know what the assumptions are built in there. And therefore you know when to use what algorithm, because the assumptions either match or don't match. Right? If they don't match, in this particular example, if you don't really understand what's going on in PCA, you might pick PCA for this, and you end up with this result. And when you try to use SVM to separate them out, you're going to be really confused, right? And just don't know what's going on. But if you understand what PCA is doing in the background, you would be like, well, this is probably a bad idea. You don't want to use PCA. What you want to do is LDA, and voila. So this is the difference between a noob and a boss. Okay? So do take your time to really understand the math behind them. Okay? That's it for today. See you next time.